Welcome to this lecture on organometallic chemistry. Today's topic is very interesting one. It is about reactivity of organometallic compounds. Now, reactivity is something which distinguishes organometallic compounds from other compounds, because they are extremely reactive with air and moistures, and they often are synthesized in the exclusion of air and moisture. They are extremely unstable under ordinary aerobic conditions. So, detailed know-how is required in handling this compound. Now, in the beginning, it was thought that the extreme reactivity of organometallic compounds are probably of thermodynamic origin, that is, they are unstable compounds and that they tend to degrade quickly. But later it was found that they are their degradation is not due to thermodynamic instability, or rather of kinetic origin, and that can be gauged by looking at the bond energy of organometallic compounds. The bond energy of the organometallic compounds depends on the strength of the metal carbon bonds, and metal carbon bonds bonds are sort of weaker than that of the metal oxygen, metal nitrogen, or metal halide, or other metal heteroatom bonds. Now, furthermore, it was seen that when you have a multiple ligand attached to metal, that their bond dissociation energy may not directly correlate for each bond dissociation. For example, for dimethyl mercury, the first bond dissociation of methyl mercury methyl bond is about 214 kilojoule per mole, and the second bond dissociation of mercury methyl is much lower, about 29 kilojoule per mole. So, what it tells that the two bonds of mercury, as they dissociate by themselves, their bond dissociation energy varies, and that depends on the intermediate species which is formed after the dissociation of the first bond. Thus, in overall, the LNM CX3, where we have a metal and then the ligand substituents on the metal, and we have X substituents on the carbon, its bond dissociation energy or this is commonly referred to as BDE, depends on the oxidation state of the metal, which is this, ligand environment, around metal, which is this, then nature of X, which is this, and in addition to all of these, overall steric and electronic effect, which is kind of very interesting. that and electronic effect. This overall steric and electronic effect arise because of the presence of the substituents Ln and X and their mutual interaction among each other. So, all of these influences the bond dissociation energy of the metal X bond, and that is why it becomes very interesting. Now, let us take a look at this bond dissociation energy and sort of classify them where how the bond stands. For example, this bond metal carbon bond energy can vary a wide range. It covers wide range. Let us say for BMe3 and arsenic Me3 and bismuth Me3, the metal carbon bond dissociation energy in kilojoules per mole stands at 365 to arsenic, this is much lower in the periodic table, to 229, to this one being the lowest as 141 kilojoules per mole. And what it signifies that 365, this to be a very strong bond, this being medium, this being a weak bond. So, the range in which a covalent metal carbon bond arise can vary a lot from being very strong to very weak, and for non-metals that depends on the location of the metal in its periodic table. Now, for the other kinds of bonds which are mainly ionic bonds, for ionic bonds the bond energy depends on the type of the metal, and the metal has to be electropositive one. When the M is electropositive, so these are mainly alkali metals. And the ligand has to be a carbanion. Ligand has to be a stable carbanion. So, examples of this include various ionic compounds. For example, we have so here we see a very electropositive alkali metal, and here is a stable carbanion. Structure of this anion is this conjugated cyclopentadienyl anion, which is very stable. Similarly, if we take a look at other ionic compounds, for example, potassium CpPH3 minus, here the metal is again a electropositive metal, potassium, alkali metal, and anion also is a stable carbon ion. So, the carbon negative charge on the carbon is stabilized over 3 phenyl rings. So, what we see that for ionic compounds, the metal has to be a electropositive ion and the anion a stable one. Another example is the sodium acetylide, where this sodium is again a electropositive metal, and this acetylide moiety is also a stable carbon ion, where the anion is stabilized over a sp carbon atom. So, there are cases where multi-center non-classical bonds are formed. These MC bonds generally forms of atoms like boron, electron deficient atoms like borons, aluminums, and these are generally referred to as electron deficient bonds. Or non-classical bonds. Because they do not follow the conventional view of two centered 2 electron covalent bonds. Now, in this case, where non-classical bonds are formed, multi-centered non-classical bonds are formed, the valence shell of L is usually less than half filled. M valence shell is less than half filled, and M is a polarizing, strongly polarizing cation, is strongly polarizing due to high charge to radius ratio. So, that means that these cations are very small, and hence we see the examples of this class includes methyl lithium, dimethyl beryllium, trimethyl aluminum, which is a dimer, as opposed to potassium 2N HN plus 2N plus 1 anion. Now, what we see over here, that except for potassium, which is large, other metals are very small. They are very small, and hence the cations which are polarizable, they have less than half filled, they conveniently formed multi-center bonds. So, all of these forms multi-center bonds, electron deficient bonds, whereas when the metal is large and it is not as polarizable as the other one, then this is forming ionic bonds. So, what we see is that depending on the size and the polarizability of the cation, the organometallic compound can have non-classical electron deficient multicenter bonds, or it can also be truly ionic ones, and hence the reactivity of this species would also vary accordingly. Now, another important concept involving organometallic compounds is its 18 valence electron rule. So, this is an important rule that says that transition metal complexes, one which are stable ones, should have 18 electron in its valence orbitals. And this rule have often been used conveniently in stating that certain compounds could be prepared because they would meet the 18 valence electron rules, and sometimes erroneously it is said that compounds which cannot have 18 valence electron rule would be unstable and hence cannot be prepared or dealt with. However, as a lot of organometallic compounds were synthesized and their structures and interactions were looked into, then it was found that there are compounds which obey 18 valence electron rules and there are compounds which does not obey 18 valence electron rule. So, first of all, we would take a look at 18 valence electron rule and see what are the compounds which obey them and when the 18 valence electron rule is not obeyed. And gradually we move on to the classification based of this kind of organometallic compounds. And usually it is found that there are 3 types of compounds: class 1, class 2 and class 3. So, let us see and analyze what is 18 valence electron rule and what are the different classes of 18 valence electron rule that we just has described. Now, in order to understand the origin of 18 valence electron rule, we should understand what leads to the concept of 18 valence electron rule, and that stems from the fact that this rule is primarily applicable for transition metal complexes. The reason being that transition metal complexes have d orbital which leads to larger number of valence electron. For example, a main group element uses only ns and np orbitals for chemical bonding. So, the number of orbitals used is ns has 1 orbital and np has 3 orbital, leading to 4 valence orbital which can have 8 valence electron. So, main group elements primarily would follow that 8 electron rule for its stability. Similarly, for transition metals, they have inner d orbitals. They use n minus 1 d ns and NP orbitals for bonding. So, it has providing 5 orbitals, Ns providing 1 orbital, and Np providing 3 orbital, giving a total of 9 orbitals, which can accommodate 18 valence electrons. Now, the question arises that for a transition metal complexes, are all these 9 orbitals fully occupied or not? Now, it turns out that these orbitals need not be fully occupied and they can be partially filled, can be partially or fully occupied. Now, this is a very interesting concept, the concept of partial occupancy of this orbital, because if it is these orbitals are partially occupied, then they can accept electron, and if it is fully, as well as they can donate electron. And this is a unique characteristics of the transition metals which has d orbitals, and this partial occupancy gives rise to very interesting interaction that manifests when it binds to the ligand in the form of sigma donation as well as pi acceptance synergism. The partial occupancy to sigma donation and pi acceptance synergism. So, this sigma donation and pi acceptance gives rise to various reactivity attributes. For example, this partial occupancy leading to sigma donation or pi acceptance can give rise to variation in coordination number, and in terms of reactivity, what it means that as the coordination number is changed or variation of it is allowed, then the metal compound can show chemoselectivity, manifests into chemoselectivity. Regioselectivity, and stereoselectivity. So, this is indeed a wonderful reactivity pattern that arises out of this or variability in coordination number of transition metal, and which in turn arises from sigma on its ability to undergo sigma donation and pi acceptance property of its orbital, the valence orbital. So, what we came to know today is that there is a significant amount of interactions which arises due to partial occupancy of the metal d orbital, and this leads to such kind of sigma bonding and pi bonding. Now, sigma donation of metal, let us say we have a metal carbon bond, it can have an interactions like sigma interactions as well as pi interactions. The sigma interaction is usually from ligand to metal. And whereas the pi interaction, usually called back donation, occurs between metal to ligand. So, what does that mean? That the ligand orbital in sigma interaction, ligand orbital is filled and metal orbital is empty, whereas in pi interaction the metal orbital is filled and ligand orbital is empty. So, what happens over here is two opposing electron donation that happens between the metal and the carbon. In the first one is the sigma interaction, where a filled ligand orbital donates its all these electron to the metal, and in return the metal gets electron rich, and through its pi back donation orbital, a filled metal orbital then donates onto the vacant ligand orbital. And these two, forward donation and backward donation, are symbiotic in nature. They sort of reinforce each other. As a result, they make the bond all the more stronger. I must say that this sigma donation and pi back donation synergy is a feature which is unique to transition metal complexes, and hence something which is unique to organometallic chemistry. Usually such sigma donation and pi back donation are rare for non-metals as well as for alkali and alkaline earth metal. So, these makes transition metal complexes unique, and as well as they exhibit several properties in various important transformations. So, with this I would briefly summarize today's the highlights of today's lectures, in which we have looked into the reactivity, we have also looked into the metal ligand interaction, we have looked into the directions in which the electrons flow from the metal to the ligand and the ligand to the metal, and we have also looked at the reasons which leads to such synergism that happens between metal ligand interaction, leading to sigma donation and pi back donation. Now, with this foundation in place, we are going to take a look at another important principles that in the next lecture, that is about the compounds or classification of the compound based on the 18 valence electron rules that we have learned today. We have also learned the origin of this 18 valence electron rule and how they come about in transition metal complexes. So, with this, I hope you enjoyed today's lecture, and let us look forward to the next lecture, where we are going to look at the classifications of 18 valence electron rule based principles in various organometallic compounds. Thank you.